So this is lesson 12.2a, and this is called ellipses and hyperbolas. And we have been doing parabolas, and remember, parabolas look like this or they look like that. Well, hyperbolas are going to look like this, something like that or like that, and that's both this and this together, not just one or the other. Okay, so the formula for an ellipse looks like this: x squared over a squared plus y squared over b squared equals 1. Alright, so in order to graph these ellipses, we're going to have to get our quadratic equation in that kind of a form, because the distance from here to here, let's do that in blue so you can see it better, that distance from there to there and from there, the origin to here, is going to be the square root of, or is going to be a. So if this were 25, a squared equals 25, the square a then would equal 5. So 5 would be from here, come on arrow, from here to here, and from here to here. B then would be the distance from the center to how high it goes, or from here to here. So see, this one's 25. So the bottom is going to be the square root, or the right to left is going to be the square root of the 25, which is 5. And this one's going to be the square root of 9, which is 3. So that gives you 4 points. When you write it in this form here, we've got this one, this one, this one, and this one. And that's all we're really going to be concerned with. We can put numbers in here and like put 0 in here and then find out what our y equals, and then we get a couple more points on this here, but we're not going to go too deep into that. So that is an ellipse. So let's start with an equation. Alright, so example 1. This here is our problem. This is what we have to get our equation into so that we can actually graph it, because that's what they're asking us to do, is graph it. Alright, so we need to get it into this form. Okay, so we've got to make the 36 into a 1. So the best way to do that would be to divide everything, both sides, by 36. And then that will turn into a 1. So what we end up with is 4x squared over 36 equals 1. And then we take 4 over 36 and get 1 over 9. And then the x squared. And 9 over 36 is 1 over 4. And then we don't need to show this 1 up here. In there. It's in the correct format that we want. So then when we graph it, it's going to look like that. Our first term that we have here is going to be the square root of 9, so from here to here is 3. And this is the square root of 4, so from here to here is 2. So 1, 2, 3, 4, and we can draw our ellipse based on that information. Okay, so let's jump to hyperbolas. And before that we start, let's go ahead and write our formula for an ellipse again. Okay. And then let's write our equation for hyperbola. Now notice everything is the exact same except that. Okay, for a hyperbola we have a negative. For a ellipse we have a positive. That's the only difference there. Alright, so as far as the equation is concerned, but as far as actually drawing the parabola, or I'm sorry, the hyperbola, takes a little more effort. Okay, so let's go ahead and use x squared over 9 minus y squared over 4 equals 1. Okay, so we've already set it up. And this is what we've got then for our parabola. I keep saying parabola, I keep getting them mixed up. It's hyperbola. Alright, now notice what we've got here. This is very, very important, and you'll be using this in upper level math. This little rectangle right here is very, very important. Okay, and we can draw that rectangle based on this equation there. Alright, so let's look and see what happens. So again, like when we were doing the ellipse, we would take the square root of that, and that would be the xy axis. So we're going to take the square root of 9, and that tells us we go over 3, over 3. Square rooted 4, up 2, down 2. And because of that, we can draw a rectangle. Okay. Now the rectangle vertex of the hyperbola is right there and right there. It never comes inside the rectangle. And also, if you draw a line here through the point here, through the origin, through the point here, and continue, and do the same thing this way, you get the boundaries of this hyperbola. See, what happens is it never crosses this blue line here or this one here, and it never goes inside the rectangle. So it's real easy to draw this based on that information, and then you know there's another one on the other side. Okay, so the vertex is on the box, and it never crosses either one of the blue lines. It just goes, and the same thing here. Okay, and you have to make the sound when you're drawing it, so I expect to have you practice that. Alright, and then let's go ahead and do another one. Okay, so you'll notice this one's different. Now we'll see what's different. The y is first here, whereas in the other one the x was first. All that means is that it goes this way instead of this way. Okay, so you've got the y and you've got a 9. Okay, so again, it's under the y, so it's up 3, down 3, just like it was over here when you did it up 2, down 2, because it was underneath the y. So it doesn't matter if the y is first or it's over here. You still look at the number under there and you go up the square root of that number on the y-axis. Same thing is here. Even though the x is second, we still go back and forth. Alright, so this one, this drawing right here, I guess I wrote this problem down wrong. That should be a 16. Okay, now it'll be right. And the x, we go over 4 and over 4. And you draw your box. You draw your asymptotes, just like that. But because the y is first, it goes this way. If the x was first, it would be this way. Okay, so that's the difference between the two, is which one is first, the x or the y. Alright, so that is when the center is at the origin for a hyperbola and the origin is at the center, or the center is at the origin for ellipses. Now what we're going to do is we're going to look at ellipses and hyperbolas where their center is not on the origin. So we might get an ellipse that's clear over here somewhere, and that's what we're going to look at next, and we'll just do it on the next video.